Hi all, this is Abhay and I welcome you all to this series called United by Mathematics, wherein I discuss some elegant problems of Olympiads across different countries. So this one is from Slovenia 2010 and this involves prime numbers. So a bit of number theory will be involved. So the question says find all the ordered triplets PQR which satisfy 15Q plus 7PQ plus QR is equal to PQR. So P, Q and R are all prime numbers. They may be same, they may be distinct, but they have to satisfy this equation. So how many ordered pairs, if at all, are there? So if we look at this question carefully, I can see that so P is there, P is there. So P is there in three of the terms. So let us take P on one of the sides. And likewise, we can do this for Q as well, right? So if I take P, all the terms involving P on one side, so QR would be P times, it will be QR minus 7Q minus 15. Right, so this forms the basis of the solution. So what do we have? We have the product of two prime numbers on the left hand side, and right hand side P is a prime number, and this obviously has to be prime because the product is equal to QR. So what does this say? Since P and Q and R are prime numbers, and left hand side it is a product of two prime numbers, and right hand side one of the numbers is prime, this has to be prime, and of course one of these two factors is equal to Q and the other is equal to R. On the right hand side, one of the two factors is equal to Q, the other is equal to R because it cannot be any other apart from Q and R, right? So if we make things, so P is either equal to Q or P is equal to R. So one of these two things can happen, that is it, because Q and R are prime numbers and P is also prime number, which is on the right hand side. Right, so one of these two factors on the right hand side is equal to Q, the other would be R. So there can be two possible cases, one is P is equal to Q, the other would be P is equal to R, and let us try to solve these two cases one by one. So if P is equal to Q, since both of these are not equal to 0, I can cancel these two out. So I'll be left with R is equal to QR minus 7Q minus 15. If I take constant on one of the sides, I'll get QR minus 7Q minus R is equal to 15. Now, so this is a Diophantine equation. So if I take Q common from the first two, so it will be R minus 7. And if I try to make this factor, so minus of R minus 7, I need to add 7 on the right hand side. So this solves. So Q minus 1 into R minus 7 is equal to 22. Is equal to 22. And since 22 can be written as product of two factors in many ways, one of which is 1 into 22, the other is 22 into 1, the third one is say 2 into 11, and the fourth one is 11 into 2. So clearly, if I equate these two factors in 1 into 22, so this gives Q minus 1 is 1, and that means Q is equal to 2, and from the first R minus 7 is 22 and R is 29, and we have to ensure that P, Q and R are all prime numbers. So these two are prime, so this looks good. If I equate this to the second of the factors, so Q minus 1 is 22, so this gives Q as 23, and R minus 7 is 1, so this is R as 8. But clearly R is a prime number, but R is equal to 8 doesn't seem to be a prime number, so this gets rejected. For the third one, Q minus 1 is 2, so this gives Q as 3 and R as 18. But R is a prime number, R cannot be 18, so this gets rejected. For the fourth one, Q minus 1 is 11, so this gives Q as 12 and R as 9, will be rejected because Q and R are not prime numbers in this case. So the only possibility is Q is 2, R is 29. Also, since P is equal to Q, the ordered triplet which will get formed would be P as 2, Q is 2 and R is 29, and this triplet would definitely satisfy this equation. We can all verify this. Let us look at the second case now. So second case, we have P is equal to R. If we look at the equation carefully, if P is equal to R, these two will get cancelled out. So we'll be left with Q is equal to QR minus 7Q minus 15. So what do we have here? So QR minus 8Q is equal to 15. We take constant on the other side, and if I take Q common, this is a relatively easier equation than the previous one. Is equal to 15 on the right hand side, and 15 can be written as a product of two factors in four ways again. So 15 into 1 would be 1, 1 into 15, 3 into 5, and 5 into 3. So let us check all the solutions. So if we compare this to the first one, so Q is equal to 15 and R is equal to 9. Clearly R has to be a prime number, but R is 9 is not a prime number, so this gets rejected. So for the second one, Q is equal to 1 and R is equal to 23. 23 it will be, right? Yes. So Q is a prime number, but Q is equal to 1 is not prime, so this gets rejected as well. For the third one, Q is equal to 3 and R minus 8 is 5. This gives R is 13. So this looks good. P, Q and R, they're both prime, and P is equal to R. So P will be 13 here. So the other triplet would be P is 13, Q is 3, and R is 13. So this will be another triplet which will be satisfying this equation. We can all verify this. For the fourth case, we get Q as 5 and R as 11, and this looks good as well. So Q is 5, R is 11, and since P is equal to R, the other triplet would be P is equal to 11, Q is 5, and R is 11. So these are the possible three triplets PQR of prime numbers which satisfy this equation. Hope you've liked the solution. Take care.